Welcome. This is the second video of our dynamics cart weight Newton's second law. We're going to do the data analysis, but first I'm just going to remind you of our equation. If you don't remember this equation or how it's derived, I suggest going back over the first video. But we're going to see if we can prove this, or at least construct a graph that would demonstrate it. Okay. So here's the data one of the groups got. Now, you'll notice a few things that we need to fix. One thing I mentioned is in my method, I mixed up my masses. So mass 1 was mass 2. So we double check that. Actually, this might actually be correct. No, it was. Okay, good. That was the hanging mass. And that is the dynamics cart, because they started with the dynamics cart with nothing else in it, was 600 kilograms. No, 600 grams, but we will need to convert that to kilograms, but I can demonstrate the easy way to go about doing that in a minute. Okay, so you might also notice there's a fair bit of variation in some of these values, but you can see a rough increase for the most part as we go down. So as the mass that was hanging is transferred over to the cart, you see the time it takes to move through a fixed distance of 0.6 meters is roughly increasing in time. The total mass stayed a constant 1 kilogram. All right, so maybe over here we're going to write mass. I'm just going to call that mass 1 in kilograms. And mass, well, I actually don't need the mass 2. That's not accounted for in my equation because that's actually tied up here, which is fine. That's 1. So insofar as that goes, I need mass 1. So what I can do, let's have a look. So mass 1 in kilograms is mass 1 in grams divided by 1,000. So you see what I've done here? Oopsies, 1,000. Okay, so just equals. Once you press equals, I just clicked on this here, and I did /1,000. Okay, put that down, and we have 0.4. Brilliant. Now, if you want to repeat something for each row, just drag that square down, and there we go. We divided all of these by 1,000, so there we go. Okay. Okay, so now what I do need is I need 1 on M1. That's going to be my independent variable. So we're going to write that. So 1 on M1, that will be in inverse kilograms. Okay. So now I'm going to press equals, and I'm going to do 1 divided by this, and enter. Oopsies. Click on that one and drag. Okay, so that's the independent variable I'm going to graph. You can do some formatting to tidy up these, but I'm not going to bother with that at this point in time. Now, the dependent variable I'm going to graph, first of all, I need to work out the average time. So average. You can use the average command, but I can't be bothered, so I'm just going to parentheses. I'm just going to add these 3 together. 1, 2, 3, close parentheses, divide by 3. There we go. That's an average. Right. Again, you can round these off. You can make it round these off, but I'm not going to bother with this. Okay. There we go. So now we have all our average times. But what we're actually going to graph is t squared. So t to the power of 2, which would be in units of seconds squared, power of 2. Okay. So I'm going to take all these values and square them. Tilde 2. There we go. And let's drag those. Okay. Now, according to my theory, these will be, these two should be proportional to each other when I graph them. We'll have a look at what the results show when we graph them. All right, I haven't used Google Sheets for a while, so I'm going to do the simplest way. If this doesn't work, we'll try a different approach. So I'm just going to drag those together, and we're going to draw. Okay. Let's make a chart. We're going to do a scatter plot. All right. So I want a scatter plot. There we go. That looks rubbish. Okay, that's not what I wanted at all. Okay, so no, it doesn't. It's not interpreting what I want. So, all right. Let's start with the x-axis. Okay, I5. Yes, that's correct. All right. Now. Actually, that doesn't. No, I just clicking on that seemed to do something. Is that what I want though? Yes, it is. That is on the. That is on the. Okay, we've got 2.5 to 5, so that's an independent variable, and we've got 0.5 to what appears to be. Oh, that's. Yeah, there's our highest value, but it seems to be rough increase. I'm not sure what's happening at. What point is that? Okay, it was a general trend upwards anyway, but this seems to be an outlier here. It's rather significant, but we're not going to do anything. We're not going to remove anything now. We'll go through the reasons why there might have been some problems with the experiment in a separate video on error analysis. But you can see a fair bit of scatter. But we're going to demonstrate that a bit more. Now, we're going to improve upon this graph in a number of ways. First of all, we can't prove proportionality or can demonstrate proportionality with this graph because we actually have, it starts at 2.5. So we're going to change that. Now, I need a trend line, and I'm going to have an equation. I might show my R-squared as well for the sake of it. The R-squared is absolutely rubbish for a physics experiment, 0.46. We need to do better than this. But for the sake of learning, it is what it is. Okay, so I'm not going to bother with that. We're actually going to do a linear equation because it should be a linear graph, and that's what we get here. So we get a slope of 0.11, and we actually have a y-intercept. That kind of demonstrates we're probably not going to have proportionality with this, and there's reasons why that we'll go through, as I said, in a separate video. So let's go through the vertical axis. All right, no, minimum value is 5 for vertical axis. The horizontal axis I want to see. Horizontal axis. Okay. Let's put the minimum values at 0. Okay, with that, I mean, we don't have a lot of data out here, but we essentially extrapolate down backwards to here. We have a graph. Now, if this was true, the hypothesis, the line will be the line, we have a straight line. There's a lot of scatter here, and the line will be going through the origin. So going through 0, 0 because it's proportional, but we have a significant y-intercept. And there's a number of reasons for that. We'll go through later on. Okay, so other than that, let's put some things in here. So chart title is going to be time squared versus inverse mass. I should say inverse hanging mass. All right. Let's add the axis titles as well. Okay. Oh, you can do it all here. Okay. Horizontal axis title. Okay, so I'll say that's inverse. Actually, I'll run it. I'll express it this way: 1 on m1 in inverse kilograms. And the vertical axis. This is time t squared in seconds squared. Okay, so we've constructed our graph, and so that's our at least we've gone through and done the analysis of that. Now, looking at the graph, you can determine that we have significant random error because of the fluctuation in the data, both in the fact that we had differences within the averaging. There's fluctuation within the different series. So you look at all these, each row of T1, T2, T3, you get significantly different results. Fluctuation here, it seems to follow a general upward trend, but yeah, significant in that respect. So that's the example of random error that's demonstrated here. Systematic error could be the result of, could be demonstrated as we expected something to go through the origin, but everything's been shifted up, would be as a result of systematic error or having the wrong premises. A couple of assumptions that were made with this. One was we're going to ignore air resistance as something to be considered, and also the method that was used in this experiment, which I'm not going to go through here, but we'll bring it up again in the next video. So now we've got our data, we've analyzed it, and looks at this point in time that our hypothesis has not been upheld. So in the next video, we're going to look at the discussion. All right, so I'm going to sign this off now.